some component of the so-called chiral P-wave symmetry would appear, and at the edge or the defect of this kind of superconductor, then there might exist the so-called Majorana fermion. Majorana fermion is an elusive, we call maybe elementary particle, first proposed by Majorana, and in a simple way that it is a particle identical to its antiparticle. So, for example, one candidate would be a neutrino. Okay, but there's no solid evidence that of the Majorana fermions from the particle physics. Maybe since its invention, conceptually invention, for maybe 80 years. Okay, but probably recently this has become one of the focus areas for condensed matter physicists to try to find out the Majorana fermion in condensed matter, not in the particle physics. And one of the ways that one of the easiest way that if you have a P-wave superconductivity, P-wave, chiral P-wave, then at the edge or with the vortex or the defect, you very likely, for example, this is the P-wave superconductivity. If you increase the strength of the defect potential, then eventually, when it reaches certain bound, a Majorana fermion at the zero energy bound will form. Okay, and this not only is it intellectually interesting because it is a Majorana fermion is a elusive particle for so many years, but also because the statistic of the Majorana fermion, it could be very useful for the quantum computation. So this is one example that how new material state can bring a new possibility. Okay. There are other things. What we found out is the a possible coexistence of the superconductivity and the ferromagnetism in this bilayer system, actually in YBCO. And another thing is that this is also a spectroscopy work done in ALS. The sample again was from Taiwan, and at that time I was also at ALS. So it is that in this bilayer, something new, so-called here is a quasi-long-range electron supermodulation happened in this bilayer. Put it in a simple way, it is that the charge density wave was discovered in this bilayer system. Actually, CDW order was discovered even earlier than this paper, maybe 5 years ago or 3 years ago. But before, in the single crystal, what they discovered is a quasi-two-dimensional charge order. But in this work, that the three-dimensional CDW order was discovered. So this is again from this non-existing bilayer. Actually, very recently, many new things was discovered that in this bilayer. And since sometimes I will go to another issue. Now let's go back to some. Well, this is just some data manifest the existence of the charge order. I won't go to the detail. But let's go back to this simple picture. And it's a simple question. When the YBCO thickness is thinner and thinner, or the ferromagnetism is relatively stronger and stronger, then TCR goes down. That we know, and we can explain by the ordinary concept of rivalry between the superconductivity and the ferromagnetism. But there's a peculiar thing. You can see that actually, for example, this is the unit cell of the YBCO. I think it's YBCO. Yes. Actually, it depends on the thickness of the LCMO. In this experiment, you can see this interface, or this bilayer, always has its effect, even up to the sixth layer of the LCMO. I'm sorry, LCMO is sixth layer. But you can think about that. This is just one interface. How can it affect? How can it take effect on such a bulk YBCO? And we also have our own. So what is the real mechanism for this TC suppression in this bilayer structure? We actually go even further strong. This is our data that now we submitted this paper that we fix the LCMO at 20 nanometer, and then change the thickness of the YBCO with two termination. You can see some that even the effect actually saturated at 60 nanometer, although it becomes smaller and smaller when YBCO, the thickness of YBCO becomes larger, thicker and thicker. But it actually saturated at a very thick YBCO. So usually, and even up to now, people don't believe that such an interface would actually has a long range effect in sample. But this is not really that strange. For example, for this kind of charge density rate, it has already been a long range order. So the interface indeed can make a change of the of the whole bulk for a very long range. And we think that the reason of this long range effect is that there is some very long range charge transfer happening through this through interface. Although the detailed mechanism that exact mechanism that we cannot really point out, but we have some evidence. For example, we can measure the valence of the manganese ion. Okay, when the this is the low data, and by the energy of the edge, we can determine the valence state of the manganese ion. And you can see that here, you can see that when YBCO becomes thicker and thicker, actually it affects. This is a bulk measurement, so this is bulk data. It affects the valence state of the manganese that in LCMO. And when YBCO becomes thicker and thicker, the valence of the MM becomes positive and positive. In other words, the YBCO is taking electron from LCMO and in the bulk sense. So this is still controversial and unsettled. That I think up to now, most people believe that the interface effect is simply just maybe at most 1 or 2 nanometer. But now we are fighting for this because we believe that there's also a long-range charge. If we don't call it a charge transfer, maybe it's because of this interface, we will have some new very long-range charge redistribution in this sample. That's what we are doing. And then now we also have some new subjects that we try to fabricate new bilayer by this is actually some Nature Physics paper in 2003. It is with the idea that if I can put two kinds of doping of this is kind of this is a mother compound. This is the a mother compound of high-temperature conductor. This is the so-called overdoped high-temperature conductor. And their idea is that I put these two things. This is with no TC. This is with maybe either no TC or low TC. When they put in, they find out that there will be a TC occurring due to the combination of these two layers. I believe their original motivation trying to create a TC much higher than the bulk value, but indeed in this study they only reach the maximum TC of the bug. So I consider it a failure. But I do not think that I think we know some better way to do this. So now we are doing this probably in a better combination, and hopefully that we will eventually find out some higher TC than the bug material, than that of bug material in the future. So this is one thing we are going. Another thing is that go back to the YBCO. This is now we know that the superconductivity actually occurring in copper oxide plant, but this is the structure of the YBCO. The thing is, the idea is that with our technology, which can do the layer by layer growth, why not we just make a single layer of the copper oxide plant without all this blocking, building block, and see what's happening in this single layer, in this mono layer copper oxide plant. Indeed, we actually have already done some of them, and we on the on a substrate called STO, we grow only one layer of the grow only one layer of copper oxide plant, and then cover it with 6 layers of the STO. This is some demo of the grid that we grow one layer of copper oxide and grow 6 layers of the STO. So you can simple to us. You see it, you saw it. That's just as by your eye. And so we have already at least have some preliminary success of verification of this single layer copper oxide. Of course, we can also fabricate a 2-layer, 3-layer, and study the change the change of the property for this few layer or mono layer copper oxide plant. And there is an issue. Even if you grow a mono layer copper oxide plant, then what would be the structure? Actually, for you to get the high TC, because previously people get a high TC from this structure called a planar structure, then we would like to get this kind of structure to eventually we dope it to get the high TC. But if you look into the geometry, that actually you would have 2 possibilities for this single layer of atom. Single layer. One is so-called the chain type, that you have this one, or it could that you have this type. And again, as I just discussed with Professor Jiunn-Yuan, that none of them can be 6-fold combination because copper has to remain 2 plus. But how do you determine it? Because in this case, your sample is only just one single layer, so you cannot determine the structure by ordinary X-ray diffraction experiments, because that requires all the coherent interference that are from the X-ray and from the bulk material. So the thing that we can check it is the preliminary check is by the so-called linear dichoism of the soft X-ray spectroscopy. So we also that this is the spectrum we take. It's called dichoism, that we see the difference between when electron is parallel to C direction and the electron is perpendicular to C direction. In a way is that we can check the spectroscopy when the electric field of the soft X-ray is in this direction, we call it perpendicular to C, and if the electric field is along this direction, it's called parallel to C direction. And presumably because the asymmetry of this structure, you will see the difference of the spectrum. And indeed, that we see some small linear dichoism of this spectrum. We also do the simulation. This is for pure. Okay, let's see. This is for pure plane type. You mean in one direction. In one direction that would be this one, and in the other direction totally no intensity. And if it's a chain type, then you would have, when you have the electric field parallel to C, you would get a very high intensity. And when the electric field is perpendicular to C, you will get half the intensity. And this is our experiment. So, judge from this one, that it seems that for now we didn't. The structure is a mixture of the chain type and plane type, and by this simply linear combination, I would say that now our sample is 60% chain type and 40% plane type. But our purpose is try to control the growth parameter to try to either get the 100% plane type structure or 100% the chain type structure or both. And then we can do further things. And then when we feel comfortable, we might want to ask both of the experts that try to help us to really figure out and try to maybe find out some local superconductivity in these materials. So, show summary on the monolayer that we realize, because we know that we have grown the monolayer carbon oxide. But what are the structure and the property, and can we do it consistently? And also, eventually, when this kind of monolayer structure is available, can we, because they are presumably insulated and probably so-called insulated, then can we put the carrier in this monolayer, make it conducting or even superconducting, and hopefully superconducting advantage. That's one thing. So go back to the original theme of this talk, to create a search for quantum matter. Okay. Today I would just say that this is the way. But just as any good adventure, the safety and the success is not guaranteed. Thank you very much. This is my talk.
Okay, question or comment?
Do you still want to ask, or I have already answered your question?
But I just want to say, how do you know there's a superconductivity in the network junction?
No. Because I really go too fast, so okay, this is something I have to make it clear. Go back to this one. This is just like ordinary. This is just like ordinary X-ray diffraction paper. Okay, but simply just it can only see the order of the carbon. So it's a bulk measurement, which means that this ferromagnetism actually coexists with the superconductivity, or this small ferromagnetic order actually is established in bulk.
So, but I'm just saying, how do you know it's a superconducting?
It's superconducting because we measure it, and we know in this sample. For example, you can see that actually you can see the superconducting signal from the metallization. We measure the resistivity, so we know that for this sample, I didn't show that. For this sample, the superconducting temperature is about 70 Kelvin. It's here. And actually, you can see the Meissner effect from the metallization here. So this sample at low temperature below the 70 Kelvin, it is superconducting, and probably coexists with a small ferromagnetic order.
So it's a bulk. It's not really.
It's bulk. It's bulk. This measurement is bulk measurement. This is bulk signal. So it's bulk. And the question is that when you have this two kinds of, what I worry is that the ferromagnetic order is actually small, but it has to be small, because if it is strong, then it will kill the superconductivity totally. So I don't know if this degree of coexistence is enough to really generate the chiral wave. That I don't know.
question can explain why the interface between the two insulators is there is a high mobility. So that's the question at the beginning of the talk.
You know, I have already prepared for this question, and actually I already know what I should do. I would go to this page. Wait, and call out Professor Jiunn-Yuan. This is your paper.
Okay, a short answer to you is that the mobility is eventually very low. So the Nature paper just for one shot. And then after 2004, people realized that actually the high mobility layer has something to do with oxygen vacancies. So if you apply right growth condition, actually the mobility at this LLSTO interface is about 2 orders of magnitude smaller than conventional semiconductor. So this is just a topic for academic interest, not for real application. This is my my honest answer to you.
So what's the secret behind that?
What's the reason? The origin of this metallic behavior?
Well, it's a long story, but anyway, I think we should focus on otherwise topic, and then but I just give you a short answer here. In physics, if you want to have very high mobility, the first thing you need to have is that you have a very low rate of diffusion, which means that there is not a lot of disorders. So actually, for all kinds of oxide interface, thermal annealing is always important if you want to have good crystallinity. So you will always have an interdiffusion, and in physics language, this is a disorder. So when disorder is high, you have a no net and there's a localization. So your mobility certainly cannot get super. So in all kinds of oxide interface, the mobility is always not good. And so far, the only good one is the zinc oxide surface. And then it really has a very high mobility. And because of the growth mechanism, the interdiffusion there is not an issue. But that's another story.
So let me repeat again that if you want to create something new, you know, this kind of heterostructure interfaces is a ongoing field that I think is going to generate something new in the future. It won't die out for maybe 1 or 2 decades at least. As I say to you that you know, maybe this is not the only way, but this is one of the ways. If you want to create something new, that I want to encourage all these youngsters. If you want to really try your luck to have dreams, maybe you can consider doing this with Professor Jiunn-Yuan and Professor Choi, and theoretical with many others.
Thank you for the right advertisement. Okay, other questions and comments?
What's the application for superconductor and the ferromagnetic interface?
Application. Okay, let me just say it again. That nobody knows. Again, nobody knows. But they are dreams. It's a long distance dream. But let me just repeat it once again. Probably the answer at the top will be even clearer during the talk. That once we have this kind of coexistence, okay, there is likely the coexistence of the superconductivity and ferromagnetism. Then there is a possibility that we can generate a property called the chiral P-way superconductivity in material. And if a material is with this kind of, we call it order parameter, then either at the edge or around the defect, we would find out the Majorana which is a bizarre particle that we haven't find out. But because this weird particle does not follow either the Fermi statistic or the Bose-Einstein statistic. It has a very interesting and very useful application in the quantum computation. So if you want to ask me the application, that's one possibility that maybe this would lead to, who knows, the realization of the quantum computation.
Bound state.
It's a bound state. Indeed, it's a bound state. You would only find at zero energy. It is indeed a bound state. It has to be a bound state.
Quasi-bound state.
Well, every particle is quasi-particle, so at least in condensed matter. But usually, you know what? My point of view is that we better treat them as real particles. For example, usually we simply just think this quasi-particle conducting in metal real. But actually, they are either Hall or electron. They are just quasi-particle.
Okay, so I think it's about time. So let's thank Professor Lin again.